Coursera, we're an educational company. Our mission is universal access to the world's best education. We were founded after Professors Andrew Ng and others decided to put their graduate level courses at Stanford online and make them available for free. They expected only 1,000, maybe 2,000 people from around the world to sign up and participate. Instead, over 100,000 did. Over 100,000 people participate around the world. Coursera was born out of that. We do MOOCs, massive open online courses. It's been a little over 3 years, but we have over 14 million learners from all around the globe. We have over 1,000 courses that are available online right now, completely for free for anyone around the world. We've had over 2.2 million course completions, and we have over 120 partners around the world. These partners include names you may have heard of them like Stanford, Yale, Princeton, the London School of Economics. These are top quality courses, and they're available for free. We started out from fairly humble beginnings with a simple ELB, PHP, and MySQL RDS database behind the scenes. The picture that you cannot see at the moment, however, you couldn't see even if the screens were working because it's grown very substantially since where we started. We have a huge number of services, trendy these days to call them microservices. We just call them services because there's less syllables and that's better. But today we don't want to talk to you about our web stack, our Scala-based serving systems that power the main web experience. We want to actually talk to you about two subsystems that we call Iguazú and Grid. And they are our batch computing environment and our programming assignments grading environment. So with that, I'd like to invite Frank up here, one of our founding engineers, to tell you about Iguazú.
Thanks, Brandon. Cool. So before I start talking about how we use Docker and batch processing for, so just to give you a flavor of what batch processing enables us to do. So the first big category is reporting. So for instance, we generate internal reports, things like business metrics, things like payments reconciliation, making sure that what our payments processor has and what we have, the records are the same. And if not, send out emails warning people and things like that. We also do, in addition to that, we also use this to generate instructor reports. For instance, if the instructor wants to see the grades of, for instance, everyone in his class, what happens is that there might be 50 or 100,000 students in his class, and that's not going to take, that's going to take much more than, say, 5 or 10 seconds to generate. So you have to offload this to a batch processor. The second big thing that we use batch processing for is marketing. So we use ECS actually to send out all our recommendation emails. If you have a Coursera account, you might notice that we send out a weekly recommendations email with the list of courses that might interest you. So that is actually triggered from Docker. We also do like specific batch marketing and reactivation emails through our batch processing framework. And finally, the last thing we can do is that because we are an education company at heart, we always want to figure out ways to make our learning experience better. So part of this includes auto-graded programming assignments, which Brandon will talk about later. And this also includes peer review matching, peer review analysis, things like that, some machine learning stuff that goes in that we also are using batch processing for. Great. So next, bad old days of batch processing. So this was before we got access to ECS, before we got access to Docker. So we had this thing called Cascade. So Brandon said that we have, so for our first version of our learning framework, we used a PHP-based, basically a simple LAMP stack. So back then, I was a new, junior software developer. I decided it might be a good idea to write our job runner framework in PHP. And let's run it in a screen session because that's great. It's easy. For me back then it was easy to control and things like that. Now I know better now, but this was what happened. So what happened was that it polled for new jobs, and basically it pings the SQS queue once every minute and polls for new jobs. And basically in the end the result was that it was fragile, it was unreliable. PHP is pretty good for writing on-demand web applications, scripts that run for 1 second, gives you some HTML output and quits. PHP is not so good for things that take 5 hours to run. For one, it has a lot of memory leaks, and which meant that sometimes the Linux kernel will kill your job before it finishes, which is not good. And so we had to do do interesting things like, forcing a restart on a regular basis to make sure that, our scripts don't run out of memory in the middle of a job. So that was not good. We tried again. So we came up with something called Saturn. So Saturn, this time around, is Scala and JVM based. So that's better than PHP. And this is powered by an actual scheduler library. So in this case, Quartz. So some of you might have heard of Quartz. This is basically allows you to just basically run functions, run Java functions, or run Clojure functions or Scala functions, once in a predetermined schedule. So that's good. But there are also limitations. This system can only run cron jobs. It cannot run jobs on demand. So if instructor wants to generate a report, you can't do that. So developers ended up having to write workarounds, such as having a job wake up every 5 minutes to check whether there are new jobs. And if there are, do it. If there are not, just go back to sleep. So that's not great either. And the other thing is that all jobs ran on the same JVM instance. So that's great if you have one job running on a JVM instance, because you can get to use all the CPU and all the RAM that the machine provides. Not so much when you have to run 10 or 20 jobs simultaneously. What happens is that then you have CPU contention, you have memory contention, sometimes you just run out of heap, and then all sorts of bad things happen and your jobs fail. So that's not good. So really, after 2 not so successful attempts, we sat down and we decided, we wrote down all the things that we want out of a system like this. So first, reliability. So Saturn and Cascade, they were flaky. Developers, instructors, our learners were frustrated with jobs not being able to run properly. So we wanted something reliable. Secondly, we want something that's easy to develop for. So both Saturn and Cascade had development problems. Developing and testing locally was pretty difficult. And we decided that little to no boilerplate code should be required for developing a new batch job. We wanted easy deployment. So deployment was also difficult, and was also difficult with those two systems. For Saturn, our PHP-based process, the deployment process was logging onto the machine and Git pulling the latest code. That is not good. We also developed a set of very nice tooling for deploying our online services, such that you can deploy an online service with 2 or 3 clicks. So, developers started asking the infrastructure team, all your other services can have one-click deploy tools. Why can't your batch processing service? So that's what we wanted. We wanted something that's, we also wanted something that's high efficiency. So, we are a startup. We're not making any money. There's no surprise to anyone. So we are cost conscious, right? So most jobs complete within 20 minutes. But if we just launch new EC2 instances, what happens is that EC2, Amazon charges you for the full hour, whether you use, 5 minutes or 50 minutes. So, that's not going to be efficient for us if we just start launching new EC2 instances. And the startup time of individual instances can be, 2 or 3 minutes at sometimes. So this is too long for something that may only run for 30 seconds. So that's not really what we want either. And finally, we wanted a very low ops load. So Coursera has about 60, 70 engineers. We only have one DevOps engineer, and he's currently on holiday in France. So, he can't manage everything. He can't manage our entire fleet. So we have a tradition of developers owning their services, but then developers are developers. They're not, ops people. So they don't really want to actively monitor their service and babysit them and make sure to restart it when things go wrong and things like that. So we wanted something with a very low ops load. All right. So we looked at some alternative technologies. So first, we have the homegrown stuff, Saturn and Cascade. So, that's not great. So next, we look at Mesos. Mesos is actually very powerful. So the framework's very powerful. You can extend it in all sorts of ways. But it is very hard to productionize. So especially with someone for a startup like us with no, previous Mesos experience. So, we decided that you probably do need an actual DevOps team. If you're the size of Twitter, if you're the size of Facebook, Mesos is probably very good. But the thing is that you actually need a DevOps team, which we don't have. We also looked at Kubernetes back then. So Kubernetes, I'm not sure what the state is today, but back then it was Google Cloud Engine was first class, and everything else was just sort of tacked on. So but we run everything on AWS, so that really wasn't an option for us. And then during reInvent last year, Amazon launched ECS. We are like, yes, this is exactly what we want. So it is a low to no maintenance solution. It's integrated within the AWS infrastructure. So we can use things like IAM instance profiles and things like that to just integrate it into our security framework and things like that. And the APIs are very easy to understand and very easy to program for. So that's great. However, ECS doesn't provide some things that we want. So it doesn't have scheduled tasks. You can tell ECS to just launch something, launch a task invocation immediately, and ECS will go do that. It doesn't currently have the ability to schedule something to be run sometime in the future. It has no fine-grained monitoring of tasks. ECS tells you whether your task is pending, running, stopped. So that's the three things that ECS tells you. So there's no really fine-grained monitoring, what's the task doing right now. There's no retries or delays when the cluster is out of resources. It will just say failure. So that's not great. And finally, it doesn't integrate well with our existing. So we have a very extensive set of Scala APIs and Scala tooling. And unfortunately, the ECS API is great, but it doesn't currently integrate well with our Scala APIs. So we wrote something. Being developers, we decided we wanted to write something. So what we wrote is called Iguazú. So it's named for Iguazú Falls. It's the world's largest waterfall. And the other reason why we named it Iguazú is because Cascade is a small waterfall and Iguazú is a big waterfall. And so it's a batch task scheduler. So it has three options. Basically, you can schedule tasks immediately. You can schedule tasks at a certain time, say 6 hours later. And you can also schedule it recurring. Basically, you can give it a cron string and you can schedule something, once every 5 minutes, once every 24 hours, only on Mondays and Fridays, and things like that. And it is programmatically accessible via our standard API. So that's great. And I will show you some examples of that later. And this is some semantic guarantees that we have. So things like we wanted at most once execution for our jobs. So sometimes, if your jobs can't get executed, that's fine. So we just wanted at most once execution. Jobs must be provided with at least the CPU and RAM they requested. And finally, the scheduler might also, this is sort of a rehashing of the first point. So the scheduler might also elect to, reschedule some jobs or just skip some jobs under, bad conditions when the cluster is down, for instance, or AZ is down, and things like that. So this is our basic architecture. It's really simple, actually. So basically the center, two boxes, is the Iguazú service. So the Iguazú service is a front end and a back end. So the front end is basically all the API interfaces. So developers and learners through other services can talk to Iguazú to schedule jobs. And the back end actually talks to the ECS API to actually attempt to schedule the jobs. Basically what the front end does is that it receives job requests and just puts them in SQS queues and just hands it off to the back end. The back end pulls the SQS queues and then attempts to run the tasks via the ECS API. So if the cluster doesn't have enough resources and things like that, what happens is that the backend will actually try again 1 minute later, 2 minutes later, 4 minutes later, and so on. And it also keeps track of task statuses. So once a minute, it will wake up and it will poll the statuses for all the currently running tasks on ECS and updates the data store that we have. We use Cassandra internally, so it updates Cassandra so that the front end makes those statuses available to consuming services. All right, so this is just some screenshots of admin interfaces. So this is thanks to another of our developers, Brian, actually, who made this very pretty interface. So this is basically our scheduled cron jobs interface. So you can see that we can just enter a cron expression. It will tell you when the next invocation is and things like that. This is also another screenshot of admin interface. So in this case, we are running a job called peer review metrics. We have an invocation time here, and the job status is successful. So this is just some screenshots of our interfaces. And for developers who want to develop Iguazú tasks, now it's really simple. So now you just go into our code base, just declare a class that extends an abstract job. And basically, you can declare how much CPU you want, how much memory you want, and you just write one function, run, and then it runs your job. So it's great. Running jobs locally also became much simpler for our developers. So SBT is a Scala build tool, so it's the standard build tool for all Scala services. And basically, you could just declare, OK, I want to go into this project. I want to run a sample job with a sample JSON file as parameters, and then it starts running. So 3 lines, you get your job to run. So that's great, too. And running jobs from other services is even easier. So we have an internal REST framework called NapTime, right? REST, nap. So our internal REST framework is called NapTime, and basically this encapsulates all the dirty work of actually, finding a server, opening HTTP connection, and things like that. So that for most developers, what happens is that you can just get an invocation client, and then you just do .create, and then you pass it in a request, and it will just start running our job. So that's very simple. And deploying is really, really simple. It's probably one of the simplest of all our services right now. So it's just basically merge into master. That's it. For most developers, it's just merge into master. Jenkins will watch the directory for any changes. If there are, it will automatically build a zip package, prepare a Docker image, push the Docker image into our private Docker repository, and register any updated tasks with the ECS API. So that's actually really simple for us as well. And finally, I want to talk about logs and metrics. So for logs, what happens is that logs are just stored in var-lib Docker containers. So we just upload it, for now, we are just uploading it into a log analysis service. So we currently use Sumo Logic. You might be using Loggly or any of the other various services out there. So what happens is that we print out the task name and task ID at the start so that developers can search for what went wrong very easily. And this is not the best. We want it to be more integrated with the Iguazú system itself, but it's good enough for now. So developers are not complaining too much about this. And the same thing with metrics. We are using a third-party metrics collector called Datadog. And what happens is that we provide metrics for both tasks and container instances. So tasks can define their own metrics, saying that how many items are processed and things like that. And the container instances will have metrics like CPU usage, RAM usage, disk usage, and things like that. And we found that for logs and metrics, so long as you can talk to the internet and are willing to use third-party services, things will work out pretty well. And I want to invite Brennan back up to talk about programming assignments.
Coursera. We have over 1,000 courses, and we have many of them in very technical fields. I'll give you a few examples. We have an Introductory to Programming in Python course. We have a very sophisticated complete tutorial in functional reactive programming written in Scala. We have full-stack web development that uses Ruby on Rails and JavaScript. We have very advanced courses that require the use of GPUs to do parallel programming. And finally, the start of it all, machine learning, which uses MATLAB. We need a programming environment and a grading environment that supports all of these different scenarios, all these different tools, all these different systems. So what does a programming assignment look like to one of our learners? This is an example of a programming assignment in a course that's going to launch actually this coming Monday. And this one's an Introductory to Programming in C++ from PKU, Peking University. Here, you download some starter code and you write a little program that paints some squares on the screen. And when you're done, you can submit it. Very simple upload interface. But now what happens? Grading programming assignments is a special case of batch processing. We need to provide real-time feedback as quickly as possible. Our SLA is under 30 seconds. That said, we are running completely untrusted code. We're running test cases, we're compiling it, we're running a whole bunch of stuff on it that these graders can do. It's not going to fit in the standard request response cycle, and we need to have things be incredibly secure. Anyone in the world can sign up for a course on Coursera, anyone can submit an assignment, and so therefore we have a huge number of infrastructure security concerns. Docker in and of itself is not secure. So we have a number of work that we need to do. We have actually two threat models. The first one is we need to avoid turning into Bitcoin miners, and we need to avoid turning into part of a DDoS attack. That said, we also have a second level of security concerns in the form of our instructors put a lot of work in their test cases and their test suites for the submissions. We need to do what we can with the help of our instructors to minimize the ability for exfiltration opportunities, so for someone to steal those test cases. We've come up with a system we call GRID, or grading inside Docker. So this is its basic architecture. It actually builds on top of Iguazú, our batch computing environment. One important detail that I'd like you all to note is thanks to AWS, and because everything is totally virtualized, we're able to actually run all of our programming assignments not in our production environment, in our production AWS account, but in a completely separate AWS account. This gives us a huge amount of confidence that we will be able, that no matter what happens to our containers and our servers that are executing this untrusted code, they will have no access to our private information no more than any other computer on the internet. And that gives us a huge amount of confidence. If we were trying to do this in our own data centers, it would be a huge nightmare. But within AWS, because things are cloud native, things work really, really smoothly. We only communicate to the grid AWS account via Amazon S3 and Amazon Elastic Container Service. So our control cluster, when a new assignment comes in that needs to be graded, we'll store this assignment submission in Amazon S3, and we'll tell through Iguazú to schedule the grading task. This then launches on one of our workers, and our workers communicate the grade back through an Amazon SQS that's not pictured here. We've already talked about a batch computing environment, so what's different about grid? So first of all, we adopt a defense in depth posture for security. Docker in and of itself is not secure. There are a whole number of best practices that we do, therefore, to try and make and mitigate any potential security vulnerability that is exploited in any one of our systems that we use, be it our instructors submitted grading scripts, be it Docker, be it the Linux kernel. Let me walk you through some of them. First, from the network level. I've already mentioned that we separate things into a separate AWS account, but we also aggressively take advantage of network ACLs, routing tables, and firewalls, both on host as well as on network in the form of security groups, in order to mitigate any sort of attack that may be done. So if you can't exfiltrate information via the network, because the network won't let you, that it immediately prevents whole classes of attacks and DDoS attacks. On the host level basis, we've tweaked the Linux kernel a bit. We also run AppArmor, a mandatory access control system and framework for Ubuntu. And finally, we use ButterFS to underlie the file system on our containers, and that gives us a number of extra things like file system quotas for the different containers, among other things. This is important because you don't want a submission to eat up all the file system and prevent and mess up the grades for other submissions that are running, say, on that same machine. Finally, we've done a bit of work with Docker itself in order to try and harden Docker itself up as much as possible. When an instructor uploads a cleaning script, we actually process it, when an instructor uploads a grading script, we process it to clean it. We do a number of things. One that I'll highlight right now is that we actually remove the SUID bits, the set user ID bits, on all binaries. And this is a way to prevent certain classes of root escalation vulnerabilities from being exploited inside the containers. We also run all the submissions not as root inside the container. Again, another level of mitigation that we're adopting in order to make this environment as secure as possible. In order to support, however, things like AppArmor or other sorts of things that we do within the containers to make them secure, we've actually had to fork the Amazon ECS Agent. This is the Go process that runs on all of your ECS instances and is what launches the Docker containers on your EC2 instances. So we have two forks. One is a privileged fork that sets the privileged Docker flag, and this enables us to run Docker inside of Docker so that we can clean our Docker containers inside a Docker job that itself is actually running on Iguazú. If you've got that all straight, congratulations. The second fork that we have is one that really locks things down. So that sets the AppArmor profile, it sets some networking, disables some networking things. They're actually totally open source and available on GitHub. Feel free to check out them right now. We're a little bit behind Amazon's master, but they're working very well for us right now. A gratuitous screenshot of our admin interface that you can see how we can control our clusters, launch new underlying hardware when we need to upgrade the OS, upgrade the kernel, upgrade some of our other systems that make this grading environment work. It works really well. I'd like to take a step back and see how we've done. So first of all, let's talk about usage. The adoption of these tools is a huge measure of their success. For Iguazú, we've had 38 tasks written since its launch in April, in just over 3 months. And in comparison with our previous systems, this is almost an order of magnitude more than all of our previous systems. So it's much, much easier to work with, and it's been much, much more reliable. Developers are really happy. Other developers in Coursera are much happier to write Iguazú jobs, and they're able to do this without actually having to be babysat by Frank or myself, which is really great. We have 24 scheduled tasks that run regularly. And finally, we have over 1,000 task invocations every single day. This is huge adoption in comparison to our previous systems. Docker and Iguazú and Amazon ECS has been a huge success here at Coursera. Grid, however, is pre-production at this time. It's actually the first course is launching on Monday, so we're frantically getting everything ready. But we've had dozens of graders already uploaded by multiple instructional teams. Things are actually coming together really well, and we're really excited for this environment going forward. That said, our work is not done. We have a number of future improvements. We want to support true auto-scaling. We run all of our instances in auto-scaling groups, all of our online services in Scala, as well as all of our ECS EC2 instances that run these containers. That said, we can scale up easily, adding new capacity, that's great. But scaling down, not so much. We want to gracefully let the tasks that are running complete before we terminate the underlying EC2 instance. Right now, this is not so straightforward. One other thing we need to support is task prioritization. Let me give you an example. Let's say an instructional team discovers a bug in their grading container. They want to upload a new version of that container and regrade all the submitted assignments. Those assignments don't need to run with high priority. They should run only on spare capacity that we have without slowing down or impeding the progress and the real-time feedback that we provide for our interactive feedback for our users. So we want to have multiple queues in Iguazú instead of just the single one that we do, as well as figure out a scheduling priority so that if new real-time jobs come in that we need to run quickly, that we have appropriate capacity. Finally, this is for Iguazú. We want to simulate the memory and CPU limits in the dev environment. Because we don't have the strict CPU limits or really the memory limits, this could result in some developers getting an out of memory or getting killed or not having the appropriate memory when they run their job in production, and as compared to it runs beautifully in dev. We have this stuff. Iguazú's been running in production for a while. Grid is days away, hours away from being in production and supporting. We've learned a lot of things from actually putting what we've talked about into practice. So first of all, Docker instability. Docker is a rapidly evolving and changing project. For example, they changed their internal container image file format between Docker 1.0 and Docker 1.5. So we've had our cleaning script that relies on, or that picks apart these containers and enforces some of our security guarantees, we had to upgrade that, but it took us a while to figure out what was going on and why it was failing. We've had issues with Btrfs. If those of you are running Ubuntu, the Ubuntu latest long-term support release, Ubuntu 14.04, the stock kernel, the default kernel that runs with that on Amazon EC2 is not new enough to support Btrfs in all the ways that we need to support it. In fact, it gets into this funny failure mode where the disk fills up and the disk is too full to delete anything from the disk. It's sort of silly. It's fixed in later kernels, but something to be aware of when you're actually using Btrfs and Docker on Ubuntu in EC2 today. Finally, we've had some issues with disk usage. So Docker itself, who knew, has some bugs. And so if you run Docker inside Docker, it runs well except for when you try and clean things up, at which point it leaves a bunch of Btrfs logical volumes strewn all over the file system that never get cleaned up. So we ran into some disk usage there.